Because I'm outside. All right, I think we should start. And first, I want to talk about the office hour. So, as I mentioned in last class, last week, and the department, the administrator, suddenly told me that the office hour room was not allowed to use anymore. So I tried to negotiate with them and find some new room and at the same time keep our previous schedule. So, but on Friday we have to switch the time to 3 to 4:30 p.m. And by Monday and Wednesday we still maintain the previous schedule. On Monday 2 to 3:30 and Wednesday 12 to 3 p.m. But here is the change of the room. So on Monday it will be in Map Building 325, still on the third floor in another room. And on Wednesday and Friday it will be 3167. So I'm still trying to negotiate with our admin to see whether we can change this room to be 3167 as well, so such that you don't need to count whether today is Monday or other weekdays. But if there are any changes or if I successfully do that, I will I make an announcement and also update the course web page. But for now, to avoid possible confusions, if you want to go to the office hours, please double check the course web page to ensure you go to the right room. Does that make sense? Any issue? Okay, so let's go back to the slide. Oh, by the way, please keep an eye on the cameras because sometimes there could be some changes, like in office hour or extension of deadline or whatever. So keep an eye on that and look at the announcement. So today we're gonna jump into another fundamental topic in basic statistics. It's called non-informative priors regarding objective Bayesian. And when we say objective Bayesian, that means we have a subjective Bayesian. So we'll explain what is subjective Bayesian, what is objective Bayesian. And subjective Bayesian is something like those frequentists try to blame you on that. And then that comes out the objective Bayesian and comes out the non-informative priors. And then we'll introduce a very important property called exchangeability. So it is a much weaker assumption about IID. So everybody knows IID, right? Independent, identically distributed, and you can almost assume all your data set collected from practice are IIDs. But it's often not, it's often a much stronger assumption. So what if I want to weaken the assumption, so make my model more expressive, more powerful? Exchangeability is another important assumption made, which is weaker than IID and more expressive, and it only requires a symmetric density over your probability distributions, and even more important, exchangeability and the associated definite theory can be considered a justification of Bayesian philosophy. So why? Because in a debate between like Bayesian and frequentist point of view, like frequentists can criticize and argue that why do you think everything is random, right? Why can't you think like something which only God knows, but it's true, it's fixed, it's constant. You're just ignorant. You don't know that. Right? Why can you assume everything is random, right? And this can be justified by defining theory. So basically it says, okay, if you have a set of observations and they satisfy exchangeability, it's not by the exchangeability, and then I can show you that these observations can be generated through some latent random variable. Now, the random variable first is sampled from some Prior distribution, and given the latent random variable, we sample those observations. So it's kind of a mathematical justification of Bayesian philosophy. But this is not only theoretical justification, it's actually how do you extend dependent theory to array data or high-dimensional array data is actually a hot topic in Bayesian statistics, especially it's called Rush matrix or whatever. How do you model sparse graphs with non-parametric priors? But we won't cover that in this class. So here's the outline. So first we will jump to the high level and look at the philosophy for Bayesian guys and frequentist researchers, and look at their underlying difference. Right? Because those are two groups of people, they're fighting and debating over centuries. And although the research results derived from both groups have strong connections and surprisingly consistency in some sense. And then, as I just mentioned, right, because frequentist likes to criticize Bayesian, you are subjective, right? You cannot do objective things. But science, or assuming everything is objective, you shouldn't do subjective. Right? And Bayesian fight back said, I can do objective study. I can do objective Bayesian. How do I do that? I incorporate the so-called uninformative priors. That means I only get my posture from the data rather than introducing some highly biased prior distribution. And we'll see that uninformative priors is actually not truly uninformative. You cannot guarantee totally uninformative. But the idea is that you want to make your prior to be as little influential on the posterior as possible. You want to make your posterior depends on the data likelihood as much as possible. That's the way to construct uninformative priors. And to get uninformative priors is very different from the so-called subjective Bayesian. Subjective Bayesian is like I come up in my mind what kind of prior should be, right? It includes all kinds of my knowledge, my preferences, even my bias, and then I combine observed data and calculate posterior distribution. But if you want to find some uninformative prior for some particular data, you should first look at the properties of the data you have. For example, your likelihood is like location, like shift invariant, or like skew invariant, or whatever invariant. Then you need to go back to say what kind of prior when you combine with this particular likelihood, it will have least effect on the posterior distribution. So the result will be a little counterintuitive. It's not like something like uniform distribution. You will see like uniform distribution is actually not very good uninformative prior. And then we'll look at the exchangeability. What is concept of exchangeability and what is associative dependent theory? Okay. So first, Bayesian versus frequentist. So we need to first set up the environment in which we can discuss the difference, right? So just let us consider the parameter estimation problem. We consider to estimate parameter data. Data could be a vector. That's why I put it as both, right? And from a set of observed data points, the x1 to xn, again, x1 and xn can be a vector as well. And for example, let's say if my random experiment is to toss a coin, right? And what I observe is just a sequence of heads and tails. And I want to estimate the chance that you get a head. That's the parameter. And we know that, okay, the random experiments are driven by the parameters. And now we have observed data. We want to inversely infer what kind of parameters govern the generation of the data. This is a kind of a universal problem in statistics and machine learning. So let's first look at what does frequentist solve this problem. So first, frequentists assume this parameter theta, this unknown parameter theta, is some fixed parameter. There is no randomness associated with it at all. It's just some constant value, and some magic value where only God knows, and you don't know. And my task is just to find some estimation for this constant value. How do I do that? If you are a frequentist, how do you do that? Yeah, heard that, right? Maximum likelihood estimation. I know, okay, because this is a random this is a binary random variables, and it is quite reasonable to assume it's sampled from a Bernoulli distribution. Just write down the log likelihood and over all the observations and maximize the log likelihood to find out the best estimation, right? But obviously, different set of data will end up with different estimations, right? And also, the number of observations you have in hand also influence the result, right? So naturally, like you have 100 samples, you have 100 observations, your estimation will be more accurate than you only have 5 observations. Does it make sense? Another question is that, how do I quantify my confidence, or in other words, uncertainty about my estimation? How do I claim that my estimation is very good? I think everyone has learned that before, right? Confidence intervals. But here is a basic and sometimes confusing concept in learning basic statistics. Here I want to express it again because I often got confused when I was learning such kind of things. That is, the maximum likelihood estimation or whatever other estimation is essentially a random variable. So see the difference. So theta, the true value of theta is constant. There is no randomness at all. But when you utilize the set of observations and come up with an estimation, this estimation is a random variable. And then the uncertainty, the confidence level, the intervals are all calculated based on the distribution of these random variables, which is the maximum likelihood estimation. Of course, you have other estimations, blah, 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 but they're all random variables, and you want to know the confidence interval, like 95% confidence interval. You need to characterize these distributions. That's the way they typically to ask the model parameters and to quantify the uncertainty, right? Because this is the two most important tasks. First, I want to infer something I'm interested in from data. And second, I want to claim how confident I'm, or how comfortable I feel my estimation. So this is a frequentist point of view. Right now, let's look at Bayesian point of view. From Bayesian point of view, if I'm Bayesian, I would assume theta is just another random variable. Nothing different with x1 to xn. The biggest difference is that I have observed x1 to xn, but theta is unknown. So in Bayesian, in head of Bayesian people, right, they're always associated with some like machine. You consider them some like eternal probabilistic sampling machine. Right? All the data are generated from some sampling procedure, nested, hierarchical, deep procedure. How do I do that? At first, okay, how do I get the data x1 to xn in my hand? Well, first, there is random variable data. are sampled from some unknown or known prior distribution. And then given this random variable, I sample the observed data x1 to xn. That's the basic. That's the most basic like hierarchical structure, right? But in many like hierarchical nested models, we have we have many hierarchical levels, and now people call hierarchical level as deep models, but they are the same thing. So, but Bayesian guys will never consider theta as some fixed value unknown. That is just consider theta as another random variable. And then, if I want to estimate theta, I'm not gonna only estimate a point for theta. I want to estimate the distribution for theta. So what kind of distribution? Posterior, right? We have a prior distribution of theta, right? And now we have observed a set of data points x1 and xn. I want to inversely find out, given this data, what is the distribution? So you can imagine that normally there will be like a flat, wide prior distribution, but after you have seen some set of data, your uncertainty about your parameters will shrink. And then your posterior distribution will be more concentrated. Right? So, but in a nutshell, Bayesian is trying to estimate posterior distribution of your model parameters rather than some single point. And the posterior distribution, as we know, is proportional to the prior distribution and the likelihood. That means if you use Bayesian method, you need to assign some prior distribution. And prior distribution and likelihood will help you reach the posterior distribution. Then the next question is, how do you quantify uncertainty? Right? So as in the frequentist point of view, like even I get a point estimation, I need to claim how uncertainty or how confident about my estimation, right? Similar things, similar question will be asked for Bayesian, right? But for Bayesian, that will be conceptually more convenient because I estimate the posterior distribution, right? So all the uncertainties, all the kind of probability queries, chances, and the intervals are contained in the posterior distribution. Right? As long as you have a distribution, you can do whatever you want. So, highlight again. In Bayesian world, everything is random. Every variable is random variable. Parameters, hyperparameters, and observations, all kinds of random variable. So, why we intentionally consider theta as random variables? What's the benefit for that? That's some philosophical difference. So, first, from mathematical modeling, that will be more convenient. Why? Because your observations, x1, xn, are some random variables, right? When I model them, I use some distribution, which sometimes refer to likelihood and whatever. So you use some likelihood, you use some probability modeling to model your observations. But if you do not consider theta as a random variable, you have to incorporate other languages or tools to model them. For example, I believe theta is quite sparse. I believe theta is most of data entries in theta are 0. How do I encode this knowledge? A common strategy in frequentist point of view is called regularization. I put some regularizer over theta. That means when I do the maximal likelihood estimation, I inject the likelihood term. I append the likelihood term with some regularization term. So this regularization term, I want to enforce all kinds of constraints of my knowledge on that, right? But that brings that works. That often works, but that brings a problem. Right? How do you justify it? How do you claim that your such kind of incorporation or regularization term design is valid? So that stimulates another branch of research, like when I append this regularization term, whether it still obeys the asymptotic consistency and what does it affect the convergence rate, whatever, blah, 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 a bunch of theoretical questions. But from practical usage, that won't be very convenient, right? Because you use different languages you put different languages into one model. For the observations, you use probability, metric, whatever. That's one topic, right? And for modeling of your parameters, you have to incorporate other things. But for Bayesian, there's no such difference because data is running very small. The only difference is that I didn't observe it, but it doesn't matter, right? I can still put all kinds of distributions and probability measures over that, and encode my knowledge and inject my preferences through the prior distributions. And the inference is also consistent because I just use Bayes rule to calculate posterior distribution everywhere. So this is convenient template. It's convenient model template. And also when you design a model, you only need to consider, okay, how does this model, or how are the data generated through some hierarchical sampling procedure? And as to what kind of prior you want to choose, you need to think about it. Right? You need to think about according to your understanding, your preferences, and so on. That's one benefit, at least from my point of view. From Quicken's point of view, he might argue that this is too boring. Right? You want something new. The second thing is that we can make arbitrary probabilistic statement about this, because our goal is to compute the posterior distribution. If you want to compute posterior distribution, if you have a posterior distribution in hand, you can ask all kinds of probability questions. But if you use frequentist point of view, well, I think most available question will be the confidence interval. Can I ask a question like, what is the chance that the transformation of your your parameters is between some range? It's very hard. It's very hard for the frequentist to answer this question, unless they make more assumptions on that. But of course, we have issues as well, because the key problem for Bayesian is to compute the posterior distribution. Well, if you have a posterior distribution in your hand, you are the god. You are the boss. You can do whatever you want. But the major bottleneck is that most of cases you cannot compute the posterior distribution. And the third benefit, which I think is even more meaningful or important than that, it provides a robust framework to make predictions. Why? So if you use a frequentist approach to make prediction, so first I learn the model. I find the maximal likely estimation of the model parameters, and given a new data point, say x star, right? And I just use this optimal model parameters to make prediction. That's it. But if we put the prediction in the Bayesian framework, we're going to do the Bayesian prediction rather than point prediction. So basically, the prediction is under the posterior distribution of data. So you can consider all kinds of possible parameters in this posterior distribution and use every possible parameters to make prediction, and then aggregate that according to the posterior distribution. So this kind of strategy or similar strategies are used everywhere. It turns out to be more robust. That's also a similar idea to like bagging or probability bagging. It can lower the variance and to make your model to be a more robust to noises. So again, there's no free lunch. Make the Bayesian prediction is often difficult because of this equation. But all these are conceptual difference, and benefit and disadvantages are all given to you. And another criticism for Bayesian philosophy is that people say, okay, Bayesian analysis is more subjective. Why? Because the way you construct the priors, right? And you can, because of this flexibility, you can put anything into a prior, and just combine a prior with a data likelihood, you get whatever you want, right? So I wouldn't say like subjective Bayesian is bad, because it's really important in artificial intelligence. Because what is artificial intelligence? I want my machine to have some intelligence. I want my machine to learn something, right? So it always has some knowledge before we touch the data. And then we'll absorb the data and update my knowledge. So subjective Bayesian is cool, at least for artificial intelligence. But for other scientific questions, subjective is not good work. Is not good work. So, but we also have objective Bayesian. So objective Bayesian, what is objective Bayesian? Objective Bayesian is saying, okay, I won't construct my prior arbitrarily. I want to make my prior to be as little influential on the posterior as possible. I want to make my data to speak for themselves in the most degree, in the largest degree. Then that requires that introduces some actual restrictions on constructing priors. But usually, it's not to say like Bayesian has to make a lot of assumptions, and frequentist models make a lot of assumptions too. And it's not to say like frequentist is best or Bayesian is best. And there are always some like personal preferences. I'm Bayesian, but I do not require you to be Bayesian. You can be frequentist as well. And but whether using frequency or Bayesian models depends on your applications, depends on problems, and depends on your flavor. And always check your assumptions you make. So any questions so far? I hope everyone is good, because this is just a high-level discussion about that. But I believe that's important, because I do not want students to like trap into all the calculation and proof details. I want you always. I want your mind can always have these general ideas and basic principles, so that those devil details won't mislead you or make you confused. Okay. So now, to address the subjective Bayesian problem, let us talk about the uninformative priors. So here I give the definition of uninformative priors. So in many cases, on many problems, we have little idea about what form of distribution to make. So although we have spent much time talking about like conjugate prior, right? That's mainly for computational benefit. But regarding the research or regarding the problems you want to address, sometimes if you have little knowledge about a problem, it's better to not incorporate any bias or knowledge into that, right? How can I do that? That's the question the uninformative prior wants to address, right? So basically, the objective Bayesians prefer priors which has little influence on the posterior distribution. So if your prior has little influence on the posterior distribution, then we call this prior as an uninformative prior. But that does not mean your prior has no influence on the distribution. We just want to minimize the influence of the effect of the prior on the posterior distribution. In other words, we want the data to fully speak for themselves.
Is there a threshold after which it becomes informative? Or is there a general baseline? How little influence it has where it can still be categorized as informative?
That's a very good question. Most common use uninformative priors is no, but there's some kind of research on that. Like we'll briefly mention what is like reference priors. They want to minimize the relevance entropy between the prior and posterior distribution to categorize whether your prior is informative enough or uninformative enough. But that's out of scope. But what you need to know is that what's the idea on uninformative prior. Any other question? Okay. So now, according to the definition, I want to ask, what priors do you have immediately in your mind? Yeah, uniform, right? Does uniform sound good? I think it's good. It's very, very intuitive, right? So now that I don't want to put any preferences on the values that your parameters or random variables can take. Then, which will be better than uniform distribution? I'll assign in a uniform distribution, I want each possible sample value to have an equal chance to be taken. This is pretty reasonable, right? So basic idea is that now that I do not know which parameter is more likely to be sampled, let's just assume the chances are equal. That's the essence of uniform distribution. But unfortunately, uniform distribution is reasonable, it's good, but it's not perfect. It has several issues and that we need to address. So first, let us review what is uniform distribution. Right? So if your random variable is discrete, so it has a finite number of states, say k states, then the uniform distribution is a mass function. So I assign the value for each state is 1 over k. And k is the total number of states. But if your random variable is kind of real value, continuous value, it's between some finite interval, say between a and b, then the probability density will be 1 over the length of the interval b minus a. Right? Everywhere. The density is kind of uniform over the range, and we can extend it to like 2-dimensional case, 3-dimensional case, and then the density will become 1 over the volume of the space the random variable can take. Right? But the first issue shows up. What about unbounded domains? So what if my random variable belongs to the whole real domain? So I cannot designate a finite interval. How do I construct a uniform prior for unbounded random variables? The answer is no, we cannot construct a valid uniform distribution on that. But the good news is that actually we do not care. We can just assume, okay, if it's unbounded and put uniform distribution on that, we can just assume, okay, its prior density is proportional to some constant. So this is definitely not a valid distribution. But if we still plug in this into the base rule and compute a valid posterior distribution, that's fine. Anyway, what we want is just the posterior distribution, right, rather than the prior. And the prior just incorporates some properties of the parameters or latent random variables. As long as I can compute the posterior distribution, that's fine. And then we call this kind of distribution as improper prior. Why is it improper? Because when you do the normalization, it simply diverges, or you integrate over this, it's just infinity. Right? But if we can still use it as long as the posterior is proper. So in most cases, the uninformative priors are just improper priors.
Is this constant arbitrary or
arbitrary?
Arbitrary.
So it cannot be negative. It cannot be negative. It's positive.
Just a constant.
It's just a constant. Because you can assume like I have for every point in this unbounded domain, they have the same density, right? And normally you should normalize it to ensure that the whole integration is 1, right? But unfortunately, if you want to ensure everyone has the same density, you won't be able to integrate into 1. The integration is just unbounded, is infinite. Right? But it doesn't matter because when we compute the posterior distribution, it doesn't matter if we skew the prior distribution with some constant, right? So this is called improper prior because the normalization diverges and as long as posterior is probable, we can still use it. But there's a severe issue of the uniform distribution. When we use it as uninformative prior, it's called transformation variance. In other words, if you do the transform of your uniform random variable, after transformation, the distribution will no longer be uniform. It will be informative. Remember, we want to seek for some uninformed distribution. That means in all kinds of cases, it is uninformative, right? But if right now I just do a little change, I just stretch it or just take a square of it, and then the distribution becomes not uninformative at all. That's not what we want. Right? To see the example, suppose I just define another random variable eta, which is the square root of lambda, or in other words, lambda is eta squared. Then what is the density for eta? How to compute density for eta? Just follow what we have done for almost 0, right? Yeah, so now I want to switch the paradigm. So this is the transformation, right? In other words, eta equals to square root of lambda. Now, if I want to compute the density for eta, according to the formula like we mentioned before, and you have applied it in your homework 0, just the density of the eta multiplying with the absolute value of the gradient of lambda over eta. Right? This is the absolute value of the gradient. It is a vector. This absolute value of the determinant of the Jacobian. So I hope you guys have not forgotten the formula, right? So just based on this formula to calculate. So first, lambda is eta squared, but doesn't matter because this part is just a constant. Just constant, right? No matter what eta, no matter what lambda is, the eta squared is just constant. And then this part is d lambda over d eta, right? So d lambda over d eta is simply 2 eta, right? So this is constant multiply a constant 2 multiply eta. That means your density for eta is proportional to eta. Again, this is an improper prior as well, because you cannot normalize it. But is it still uniformity? No. Why?
Because it depends on eta.
Yeah, it depends on eta, right? So if it has a scalar, then you can imagine that the larger the eta, the larger the density. Right? That means it favors larger values of eta. So obviously it's no longer uniformity. So now we see the problem of like simple uniform distribution. Right? And this example also can give us an insight about the properties regarding uniformity priors, right? So if you want to construct uniformity priors, what kind of properties you want? So first, so naively, I think if you do some transformation over the random variables which come from uniformity prior, I hope that after transformation, it still will be an uniformity. It's kind of closed operation for the variable transformations. Now let us look at, this is eta. So now let's look at several commonly used properties to construct uniformity priors. And they will say that under different properties, you will derive different uniformity priors. And then we'll go to a more general prior, it's called Jeffreys prior, which is invariant to arbitrary transformations. Here we just talk about two special cases. Right? The first case is called shift invariance. So we need to first take a look at the data likelihood. The data likelihood, in some sense, in some degree, determines what kind of uninformed prior you want. So if the data likelihood takes the form like this, so lambda is our parameter and x is the observed random variable. If the density of x, in other words, likelihood takes this form, we call it shift invariance. Why it's called shift invariance? And we call lambda as a location parameter. Why it's called shift invariance? Because if we shift both lambda and x to some same amount of distance, say c, you won't change your likelihood at all. Right? In other words, your likelihood is independent from origin. It only depends on difference between your random variable and the parameter. Independent of the absolute position or starting point.
Is this the same thing as a memoryless distribution or something like that?
Yeah, it has some connection, but I don't think it's memoryless.
Okay.
Yeah. I guess you're talking about the exponential distribution, right?
Yeah.
Well, I think it's a bit different. Still a bit different. But first, at least we know if our likelihood is shift invariance, they will be independent of the origin or arbitrary positions.
Should these two constant shift be the same?
Yeah, same.
Must be the same.
Must be the same. Other means, okay, this is lambda, this is x, right? If they shift to here, the likelihood won't change at all. If you shift to here, the likelihood won't change at all. Right? It's called shift invariance. And the problem is that how can I design an uninformed prior for this shift invariant likelihood? How to construct a prior reflect the same kind of property? So basically, you can think of like that, right? If in the likelihood domain, when I shift my lambda, at the same time shift x in some particular distance, I won't change the likelihood value, right? In prior domain, I should be shift invariance as well. In terms of what? In terms of the probability mass. Like given an arbitrary interval or given arbitrary range, if I shift the range from here to here, I will require the probability mass won't change. That will be consistent with the property of the likelihood. Now here I want to emphasize a point. We want to construct a prior that reflects this shift invariance. Why? The reason comes from the definition of uninformed prior. Uninformed prior aims to least influence the posterior distribution. And how do we minimize my effect of prior? I want to behave to be as much consistent with the likelihood as possible. So if my prior behaves drastically different from the likelihood, you can imagine it will drastically affect the posterior distribution, right? But if my likelihood just pretends to be almost the same thing as the likelihood, and then it has the least influence on posterior, right? Posterior is mainly depends on likelihood, data likelihood. So that's the key idea here. That's why I ask, how can we build a prior that reflects the same property that is shift invariance? And going back to the point we just mentioned, if I want to make the shift invariance in the prior domain, I just pick an arbitrary interval or range. I want the probability mass over this range won't be changed when I move this range everywhere. Right? And now let us look at, by putting this requirement, what kind of prior can I get? What kind of uninformed prior can I get? Right? So we choose a prior that assigns equal probability mass to an arbitrary interval in V. So and as to the shifted info A plus C, B plus C. If you write it in mathematical form, just saying, okay, my integration of the density over the interval A and B is exactly the same as the integration of density over A plus C to B plus C. And then A, B, C, and both arbitrary. Let's say, yeah, but you need to ensure A must be less than B, right? To construct that interval. Now let's try to use this equation to derive what kind of prior, uninformative prior can we get, right? So the first step is to do the integration variable transformation, right? To make the second integral to have the same lower limit and upper limit in the integral. So the most commonly used approach is to introduce another variable, say lambda bar equals to lambda minus c, right? And then you just replace the integral variables with lambda bar. This is a standard process. When in a lower limit, when lambda takes a plus c, then lambda bar will take a, right? And when in the upper limit, when lambda takes b plus c, then lambda bar will take b, right? And then lambda is now replaced by lambda bar plus c, right? And d lambda equals to d lambda bar, because it's just lambda plus lambda minus a constant. Any issue with this? It's just standard calculation. Right? And now you can, to make it look better, you can just use the lambda to replace lambda bar. It doesn't matter. It doesn't matter whatever symbol you want to put in the integral. So finally, you end up with this. It's the integral over a and b, and the integrand is the density at lambda plus c. Now we require the left-hand side must be equal to the right-hand side for arbitrary a and b. That means the integral must be exactly the same for arbitrary c, right? That is the definition of uniform distribution, right? Because for arbitrary c, I mean your density values are the same. That means, okay, the density of lambda is proportional to some constant. Of course, this is an improper product. So now we can say, first, the uniform distribution is a useful uninformative prior, especially when your likelihood is shift invariance. Right? It reflects the shift invariance property, so it's good for this shift invariant likelihood, but it still has some issues, right? The issue we just mentioned that we will do like other, say, nonlinear transformations, the transfer random variable will no longer be uniform at all. Right? This is one problem. It's called shift invariance. So let us look at one example on how to make a connection from the uninformative prior to the conjugate prior, which we previously discussed. So we can look at this Gaussian likelihood, and we assume this Gaussian likelihood is mainly parameterized by its mean parameters. So let's just assume sigma squared, the variance is known, it's fixed. So we can see that the likelihood depends on this x minus mu squared, right? So it's just the instance of x minus mu, right? So it's typically a shift invariant likelihood. And obviously, if you want to assign, so this is a shift invariance density or likelihood. And obviously, if we want to assign a uninformative prior for mu, then we just assign uniform prior, right? Constant. Right? This is uninformative prior. And now, if we look for the conjugate prior for this Gaussian likelihood for mu, what is the conjugate prior? I didn't ask you to do this because I think it's too straightforward. Just leave the answer here. It's just another Gaussian distribution. You can calculate. You multiply one Gaussian with another Gaussian, and now with another Gaussian, a third Gaussian. The interesting thing is here. Sorry, this is not zero, it's infinity. If I enlarge the variance of the conjugate part to be larger and larger until approaches to infinity, then what will the conjugate part look like? So this is the density of the Gaussian, right? So the y is determined by the variance, right? So now if I make this variance to be larger and larger until infinity, it becomes like this, right? Just like you said, it becomes a uniform distribution. So this is the first interesting observation, that if I take a limit for the conjugate prior, I can sometimes end up with the uninformative prior. So this is one example for the uninformative prior based on the property of the likelihood function, which is called shift invariance. And another interesting property is called skew invariance. So what is skew invariance? If the likelihood takes the form like this, so here's assume your observation x is determined by this parameter sigma, and the form is 1 over sigma multiplied with some function x over sigma, and sigma is negative, and f normalized regularly. That means okay, this likelihood is also a valid distribution. Then we call sigma as a skew parameter, and the density x is the skew invariance. Why it's called skew invariance? Because if you skew both the random variable x and parameter sigma by a constant c, the density will not change. And we can verify this point using the formula we used before. If we first we can do the x hat equals to cx. So what's the density of x hat? The density of x hat will be the density of x times dx over dx hat, and absolute value, right? It's just the existing formula. Just apply the template, and the density of x is simply 1 over sigma, and f x over sigma, and dx over dx hat will be 1 over c, right? So next we need to replace x in terms of x hat, right? We know x equals to x hat over c, right? We just replace x with this x hat over c. Then we'll end up with c sigma. I just merge these two terms, and then multiply with f of x hat over c sigma. Right? So now who can tell me what is c sigma? Sigma hat, right? The sigma hat. So we just replace c sigma with sigma hat. Now it's 1 over sigma hat and x hat over sigma hat. So now we say the form does not change. Form is consistent. This is called skew invariance because we will skew both the random variables x and parameter up to the same constant. Your density won't change. So to give a more concrete example, this more like we'll change the unit of your random variable value, I don't want the density or probability to change. Like I want to predict how many miles my car can still run, right? And I don't want the probability distribution of the miles or distance my car can run will be changed when I switch to a metric system. Right? When I switch to kilometers, and then the distance of the distance that my vehicle can run is becomes smaller. That's not acceptable. Right? Or becomes larger. Or if you measure my height, I don't want, like when I use meters to measure my height, I become small. I become a shorter. That's not acceptable. So this is actually a pretty reasonable requirement. So the question is, given this skew invariant likelihood, how can we construct an uninformative prior? An idea. So in a likelihood domain, I just multiply the parameters sigma by some constant. Of course, I need to multiply this as well, and then it doesn't change likelihood, right? In a prior domain, naturally, if I skew the interval or the range by some constant, the probability mass shouldn't change as well. So that's the key idea. So all we need to make a little change about our statement. That is, we consider an arbitrary interval A and B, and the prior should assign equal mass over an arbitrary skewed interval A over C, B over C. Of course, C must be a positive. And we translate it into mathematical. Math, it becomes like this, right? So the integral of the density over A and B is the same as the density over this skewed range, right? A over C to B over C. And let's see what kind of uninformative prior can we derive from this equality. And to do that, again, we need to use the integration random variable translation, a transformation. So basically, I define some another variable sigma bar to be C times sigma, so that when I replace this integral with the sigma bar, in the lower limit when it takes A over C, that means sigma takes A over C, the sigma bar will be A, right? And again, when the sigma takes B over C, the sigma bar will take B. And then we make the lower limit and upper limit to be the same as the left hand side. And then in the integral, P of sigma thus becomes P of sigma bar over C, right? Because sigma is sigma bar over C. And then d sigma is actually equal to C times d sigma bar, right? Just replace it in the integral. So it becomes C times sorry, it's is right from this we can write that d sigma bar is equal to C d sigma. You just replace it, and then d sigma will be d sigma bar over C. That is the right hand side. The only difference is that I just use sigma to represent the symbol sigma bar. It doesn't matter. So now we can arrive at this equality. That is, for arbitrary C, we have a P sigma equals to P of C, sigma over C multiplied with C. Okay. So to get the general form of the P of sigma, remember C can be arbitrary, right? So I can simply set C to be sigma. You set C to be sigma, left-hand side is still P sigma. And the right-hand side, sigma over C now becomes P1, right? Because sigma over C, right? And then 1 over sigma, because C is a sigma. So P1 is constant. That means P sigma is proportional to its inverse. Any questions so far? Everyone is good, right? It's just a simple like integration, variable changes, and simple reasoning. You end up with this, right? So now we can say that to construct an uninformative prior for a skew invariant likelihood, you end up with this. So this is an improper prior as well, because you cannot integrate into one. And you can try it, but it will fail because it looks like this, right? So if you integrate this area, it looks like it's finite, but actually it's infinite. So again, let us look at a concrete example. Right? So we still look at the Gaussian likelihood, but this time we look at the prior for the standard deviation rather than mu. So assume the mean is norm, is fixed, and the prior, the likelihood of our observation x given the standard deviation is standard Gaussian. And if you write it here, you'll find this 1 over sigma, and this is x minus mu over sigma squared. Right? So comparing with the form we just mentioned, it looks like this. Right? It's just an instance of this. So obviously, this is a skew invariant likelihood. Now to construct an uninformative prior, we just make P of sigma is proportional to 1 over sigma. Right? It's just what we have derived for skew invariant prior. But for skew invariant likelihood, the uninformative prior will be proportional to 1 over sigma. But as we previously discussed, right? So usually we're going to talk about the precision. We use precision to represent the Gaussian distribution, right? So now let us consider to represent sigma in terms of the precision. That is, I define lambda equals to the inverse of sigma squared. And according to this, I can derive that the density of lambda is proportional to 1 over lambda as well. That's quite interesting. But to derive this is pretty straightforward. Just apply the formula we have used many times. You'll end up with this. And don't forget to take the absolute value, because the derivative will be negative. You need to take absolute value. But you will see that P lambda will be proportional to 1 over lambda. So now let us connect to the conjugate priors we have previously discussed. So we can construct a conjugate prior to the Gaussian likelihood. The conjugate prior is over the precision, the inverse variance, which is the gamma distribution, right? And the gamma distribution is determined by two parameters, a and b, and this is a distribution form which is proportional to lambda to the power of a minus 1, exponential to the power of minus b lambda, right? So now if we choose a and b to be 0, what to be 0? What will the conjugate prior be? So if a equals to 0 and b equals to 0, so now it only leaves lambda minus 1, right? So that means P lambda is proportional to 1 over lambda. So now we see the connection, right, between this uninformative prior and this conjugate prior. In this skew invariant case, conjugate prior, when it takes a special have a parameters that you are reduced to the uninformative prior. So this is just a very interesting connection and observations, but this is not universal. Those do not mean that, I mean, for arbitrary uninformative prior, you can find some counterpart in the conjugate part. That won't hold. So what we have discussed so far is regarding two special cases, right? One is about the shift invariant likelihood. The other is about the skew invariant likelihood. Basically, it says, okay, if I do some transformation of your random variables, it will still satisfy some invariant properties. Right? So a natural question would be like, what if I want my uninformative prior to be invariant to arbitrary transformations? Can we do that? Right. I do not want to look at this special case one by one. I want once and for all. And the answer is the so-called Jeffreys prior. So Jeffreys prior has a nice property that it will be invariant under arbitrary transformations, linear transformations, nonlinear transformation, whatever. So the definition of Jeffreys prior is like this. So again, it is in most cases is improper prior. That means you cannot integrate it to get a final value. That doesn't matter. So the Jeffreys prior is the determinant of your feature information matrix and take square root. How many of you have started to look at homework 1? Oh, nice. Nice. And then you should know what is feature information matrix, right? But here I will repeat again. So feature information matrix is the second derivative of your log likelihood, and then take the expectation on that and take negative on that. This is called feature information matrix. So it relates to the geometry properties about your probability distributions here. But here I want to emphasize, don't confuse at the expectation here. So this expectation is under Px given theta. I mean, it's the probability of the random variable x given theta. It is not about theta. So theta here is not considered as some random variable, and you need to take expectation. You just take expectation over x, and this and this random variable, this distribution is parameterized by theta. Any questions so far? And for vector case, so this is actually a hashing, right? Hash matrix, second derivative. And now it becomes, this is scalar, this is scalar. If x is vector, so you have now the homework, right? You have practice in the homework. This will become a matrix, a square matrix. It's a hash matrix. So now let us look at what will be the Jeffreys prior for some concrete likelihood. For example, if I choose binomial likelihood, right? I don't know whether it is skew invariant or shift invariant, so I don't care actually. So I just used to compute one example of the Jeffreys prior. So the binomial distribution will look like this. So I do the Bernoulli experiments for n times, and the Bernoulli distribution is parameterized by this theta, which is the chance that you get 1. So n repeated Bernoulli experiments. So x will be the number of ones. So everyone is on the same page, right? And then this is the likelihood. So because we do the random experiments for n times, and I need to first calculate how many possible experimental outcomes will contain x ones. Right? So that's why there's a combination number here. But the remaining terms is just theta to the power of x, multiplied with 1 theta to the power of n minus 1 x Now, if we want to construct a Jeffreys prior of theta, we first need to take the logarithm over the likelihood, right? So if we take a logarithm over this likelihood in terms of theta, it becomes x logarithm theta plus n minus x multiplied with logarithm 1 minus theta plus the constant, right? This constant is a logarithm over this combination number because it has nothing to do with theta, we just consider it as a constant, right? And next, we take the first derivative as a gradient. If we take the gradient of this log likelihood with respect to theta, so it's pretty straightforward. So x log theta is x over theta and minus n minus x over 1 minus theta. I need to consider the minus sign in front of theta, so I have a minus sign here, right? And take the derivative again. And remember, this is just scalar, so just simply take it, it's not a Hash matrix. So we take it again, then x over theta is now becomes x over theta squared, and take put a minus sign in front of it, and this one's here. I didn't. I think it's not necessary for me to derive it. And now we have this, right? And now we want to compute the expectation of this, and then take negative. So if you take minus sign, you can first replace minus sign with positive sign here, and take expectation. It's here, right? So remember, this is a binomial distribution. So the expectation will be n multiplied with prime for theta, because you draw the points n times. You count how many heads you have in hand. And on expectation is just the number of the draws multiplied with the chance you have. This is some existing results we have explained in the very first class. And now we end up with n theta over this and plus this, and you can cancel the common terms in both the denominator and the numerator, and end up with this theta plus n over 1 theta, and then combine them together, you get this. So it's actually n over theta, 1 minus theta, and we take square root. Now take the square root. So this will be theta. So this is a theta to the power of minus 1. And this is theta, 1 theta to the power of minus 1. And also this is, if you take a square root, come here, right? So the theta to the power of minus 1 over 2, 1 minus theta to the power of 1 minus 1 over 2. So if you look up your distribution dictionary, it's actually a beta distribution. Why beta distribution? General beta distribution will looks like this. Theta a minus 1, 1 minus theta b minus 1. So minus 1 over 2 is just 1 over 2 minus 1. And this 1 over 2 minus 1, right? So a and b should be both half.
Why were you able to replace the x with the n theta? Did you do that problem with that?
Because when I want to do the expectation, right? This is according to the definition of Jeffreys prior. I need to take the expectation over this second derivatives, and expectation with respect to the probability distribution of x given theta, right? And then when I take the expectation, so this is a expectation of x, right? So expectation of x turns out to be n theta. So do you have a question at this point?
Yeah. So why did you just replace x in your derivation?
Yeah. So this is normal results. If your x follows the binomial distribution, this is expectation. Okay. And it can be trivially computed by using the summation property of expectation. So if you do like n Bourdon experiments, right, you can report each outcome of your experiment as like x1, x2 to xn, right? x1 is 1, 0, x2, 1, 0 until xn 1, 0, and x is just summation of these n variables. Right? And now if you take expectation, just take expectation of summation, just the expectation over each individual individual binary Bernoulli variables, their expectation just theta, just as a together in theta. Yeah. So now we see that Jeffrey's prior for this binomial likelihood is just a beta distribution or beta prior. Now we want to look at what does this Jeffrey prior looks like. So the blue line is our Jeffrey's prior, which is beta half. And the red line is some more intuitive prior. It's flat. Right? I put the same mass on every point, same density on every point. So there can be some kind of barrier in understanding why is reason. What's the rationale? What's the rationale for this weird Jeffrey prior, right? To illustrate, we need to come back to the definition of uninformative prior. The goal of uninformative prior is to influence the posterior computation as little as possible. Right? How can we minimize this influence? We want to be as consistent with the likelihood as possible. So we can look at the value of the likelihood. How does the value of likelihood change according to different choices of theta? So if theta is 1/2, how does the likelihood change according to x? How will the data x, observation x, will affect the posterior? If theta is 1/2, what's the value of this? It's just the theta n, right? Theta to the power n. No matter what x you have, it doesn't change the posterior at all. In other words, when theta takes 1/2, your data has the least effect on the posterior. After data, it doesn't affect posterior at all. Correspondingly, if I want my prior to be uninformative, I want its effect on posterior to be minimal when it takes 1/2 as well. So you see the rationale here, right? In my strange blue uninformative prior, it does take the minimum value and theta taking 1/2. Because when theta takes 1/2, it has least influence on the posterior, which is consistent with data. And on the other hand, you can look at when data takes the greatest effect. When data approaches to 1 or 0, right? When data approaches 1 or 0, the tiny change of x could drastically affect the likelihood value. And the drastic change of likelihood value will affect the posterior, right? So correspondingly, you can see on the two ends of our blue curve, it has the largest effect, right? It's the largest value. So this is something like counterintuitive, but it does have some rationale. So basically, the prior here, the Jeffrey's prior here, is consistent with the data's effect on the posterior distribution. In other words, in this way, they minimize their effect on the posterior distribution because they keep the consistent with the data. Okay, I think we should stop here today, and we'll continue on Thursday. So